All right, let's dive in. Today we're tackling one of the all-time classic engineering challenges. How do you actually build a service that can go from just one user all the way to a million? We're going to start with a single computer, but what you'll see is that this journey really uncovers a massive shift in the skills that matter most for engineers right now. So let's just put the question right out there. Imagine you're in an interview and they ask you, how would you build something like a URL shortener to handle a million users? It's a super common question, and for good reason. The way you answer it reveals everything about how you think about building strong, scalable systems. Every great story has a beginning, right? Well, for any system, no matter how huge and complicated it gets, that beginning is always the same. It starts with just one server. At the end of the day, what is a server? It's really just a computer. It's a machine that's always on, it's plugged into the internet, and it has a unique public IP address, kind of like a street address for your application. This is our ground zero, the foundation for everything we're about to build. But come on, nobody wants to remember a long string of numbers like an IP address. And that's exactly where DNS comes in, the domain name system. The easiest way to think about it is as the internet's phone book. You type in a friendly name like tiny.url, and DNS looks it up and connects you to the right IP address. It's a simple but absolutely essential first step. Okay, so our single server is working great for a while. But what happens when our little project goes viral and the user base just explodes? Or one server gets totally overwhelmed. Suddenly we have to face our first big boss battle, the traffic dragon. So you've got two main ways to handle this. You could scale up, which just means making your one server beefier. More CPU, more RAM. But that gets expensive fast. It has a physical limit, and you usually have to take the site down to do the upgrade. The much smarter way, especially for a service that needs to be on all the time, is to scale out. You just add more servers. The beauty of this is you can do it with zero downtime, and in theory, you can scale almost infinitely. Okay, but now you have a bunch of servers. How do you make sure the traffic gets spread out evenly? That's the job of a load balancer. I want you to picture it like a traffic cop, standing in front of your servers. As each request comes in, it just points it to the next server in line. Server 1, then server 2, then server 3, and back again. This is called round robin, and it's a super simple way to make sure no single server gets buried in requests. All right, so we've handled the sheer volume of traffic. But now we have a new problem, speed. In our URL shortener, every time someone clicks a link, we have to look up the original URL. If that lookup is slow, the user has a bad experience. We've got to make it fast. You know, the bottleneck is almost always the database. Our URL shortener is what we call read-heavy. That means for every one time a new URL is created, it might get read or clicked millions of times. And hitting your main database for every single one of those reads, it's just way too slow. It won't work. So we build a layered strategy. It's all about speed. When a request comes in, the very first thing we do is check a super fast in-memory cache. Think of this like the computer's short-term memory. It's lightning fast. If the URL is there, boom, we send it back in milliseconds. If it's not, we check a read replica, which is just a copy of our database that only handles reading data. And only if we can't find it in either of those places, as a total last resort, do we bother the main database. This whole system shields our primary database and keeps everything feeling snappy. Okay, our system is getting pretty big. It's fast, it's complex, and you know what that means? It's a much bigger target. We have to start thinking seriously about security and how to protect our services, and more importantly, our users' data from attackers. One really powerful tool for this is called the gatekeeper pattern. Honestly, just think of it like a bouncer at a club. We stick a special, hardened server right at the very front of our system. Its one and only job is to check every single request, to validate it and to clean it up before it's allowed anywhere near our real application servers. This way, our sensitive stuff, like database credentials, stays safe. The gatekeeper has no access to it, dramatically shrinking the area an attacker can target. So, we've just walked through the architecture of a pretty solid system, but here's the thing. Designing it is only half the battle. The single most valuable skill you need to build systems like this today, it isn't just about picking the right tools. It's about how you talk about those choices. For decades, this was the gospel of software engineering. This quote from the creator of Linux himself was everything. The idea was simple. Don't talk about it, just build it. The hardest, most valuable work was the grueling process of actually writing good, clean, functional code. But if we fast forward to today, that entire world has been flipped completely on its head. A new reality is setting in, and it's this: good talk. And by that I mean strong communication, clear architectural thinking is now becoming exponentially more valuable than the code itself. So what caused this massive shift? I mean, you know the answer. It's AI. Large language models can churn out really solid code in seconds. The bottleneck isn't the physical act of typing anymore. The real work, the high-skill work, is defining the problem, designing the solution, and clearly communicating the entire plan. That old saying, 90% thinking, 10% typing, is finally literally true. And look, this isn't just some abstract theory. This is actual interview feedback from a real company. The points for improvement have nothing to do with code quality. It's all about thinking at a higher level, articulating decision points, focusing on the systemic impact, telling a clear end-to-end story. This is what separates a senior engineer from everyone else today. So what does this good talk actually look like in the real world? It means you have to shift your thinking beyond just how to implement something. You need to start thinking like an architect. It really boils down to developing these specific skills. Can you clearly explain the trade-offs of using a cache versus not using one? Can you pinpoint the most critical decision points in your design and defend them? Can you talk about how your choices affect the entire system, not just your little piece of it? Can you actually tell a compelling story of how everything works from a user's click all the way to the database and back?
At the end of the day, it's just not enough to say, yeah, we'll use a load balancer and a cache. The real value, the thing that sets you apart, is explaining why you chose them. What were the other options you considered? What's the long-term impact on cost, on security, on performance? That is the conversation that matters now.
As the simple act of writing code becomes more and more of a commodity, our value has to shift to the things an AI can't do. It can't understand the business context, it can't weigh really complex, nuanced trade-offs, and it can't tell a compelling story that gets an entire team moving in the same direction. So I'll just leave you with this question. The code can be generated. What's the story that only you can